Welcome to AI Paper Slap. Today, we are analyzing the newly released paper, LLM-as-a-Coach, Experiential Learning for Non-Verifiable Tasks, by researchers from Microsoft Research, Tsinghua University, and Peking University.
Which is an incredibly dense paper, but so important.
Very. And the core insight here is that standard reinforcement learning for post-training on open-ended tasks, well, it currently relies on an LLM-as-a-Judge.
Right.
And this judge compresses rich, multidimensional textual evaluation into a super low bandwidth scalar reward, like a 1 to 10 score.
Which basically discards valuable feedback.
Exactly. It conflates completely different high-quality responses. So to fix this, the authors propose experiential learning. They repurpose the feedback model into an LLM-as-a-Coach that distills evaluations into transferable experiential knowledge.
So it's not just a judge anymore.
Right. The policy then internalizes this dense textual guidance via on-policy context distillation, effectively increasing the feedback bandwidth by over 5,000 times compared to a discrete reward.
Which is huge.
Massive. The result is that experiential learning consistently outperforms rubric-based RL on benchmarks like Wildchat, Alpachyval v2, and WildBench, while mitigating reward hacking and improving out-of-distribution generalization.
And that right there is a fundamental paradigm shift for anyone working in alignment. We're essentially taking the optimization target during post-training and just flipping it on its head.
Yeah, I mean, instead of asking a model to maximize a highly compressed scalar value, which, is what leads to those plateauing performance metrics you see in production, we're asking a model to match a distribution shaped by high-fidelity natural language context.
Exactly. This paper isolates a critical information bottleneck in our current RL pipelines and offers a highly scalable structural fix for it.
Okay, let's unpack this, because if you are setting up training pipelines right now, you are probably hitting this exact wall.
Oh, absolutely.
To really understand why this coach framework is a breakthrough, we first need to mathematically deconstruct why standard RL, using an LLM-as-a-Judge, hits a performance ceiling on non-verifiable tasks.
Yeah, and we should contrast that with verifiable tasks.
Right, like math or coding.
Exactly.
Yeah.
When you train a model on a verifiable task, binary rewards actually work perfectly. The code either compiles or it throws an error.
The mathematical proof is valid or it's logically flawed.
Right. Literally one bit of information, a 1 or a 0, is all the optimizer needs to push the model weights in the right direction.
But open-ended, non-verifiable tasks just do not function that way. I mean, if you are asking a model to do creative writing or provide a complex explanation of quantum mechanics, there is no single correct string of text.
Evaluating those tasks requires multidimensional rubrics. Like, as the evaluator, you have to score the text for factuality, tone, completeness, organization, all at the same time.
And here is where the math really starts to work against us.
Yeah.
So standard RL reduces all that detailed rubric assessment from the judge into a single scalar score.
Right, which is a massive bottleneck.
It is. If you're using a discrete 1 to 10 score, the maximum theoretical bandwidth of your feedback channel is just about 3.3 bits per sample.
Which is virtually nothing.
Yeah. And even if you use a learned reward head outputting a bfloat 16 value, you are hard capped at 16 representational bits.
And this quantization creates a massive optimization problem, especially at the top of the reward scale. Once your RL process saturates the available reward signal, you end up with a plateau.
So you have all these different high-quality responses that get the same max score.
Exactly, making them completely indistinguishable to the optimizer, even though they have totally different nuanced strengths and weaknesses.
Standard RL is basically like a student getting a 7 out of 10 on a creative writing assignment with 0 notes.
That's a perfect way to look at it.
Like, take the paper's Morocco travel guide example. One response might get a 7 because of repetitive superlatives, like everything was amazing food, amazing culture.
Right, and another 7 might be for a complete lack of sensory details.
Exactly. But if the optimizer only sees a 7, it learns nothing about how to actually improve.
Which is the primary driver of reward hacking. The policy is just starved for actionable direction.
Because it doesn't know why it got a 7 instead of an 8.
Right, so it just drifts towards superficial patterns that inflate the scalar score rather than genuinely improving the text.
So since the scalar score is an information bottleneck, the logical next step is passing the high bandwidth textual feedback directly to the model.
But how do you train a policy on a block of text instead of a reward signal?
Yeah, that's the tricky part.
You have to completely pivot the architecture. Detail the EL mechanism here. The feedback LLM is repurposed from a judge to a coach. It looks at the prompt, the policy's response, and the rubrics.
But crucially, it does not just provide instance-specific corrections, right?
Exactly. It distills the critique into transferable experiential knowledge, reusable strategies for similar future tasks.
Oh, like in the mental wellness app example they used in the paper.
Right. The coach extracts generalized rules, like state limitations before capabilities, and pair each limitation with a constructive redirect.
Here's where it gets really interesting. Think about the sheer scale of the bandwidth increase.
It's math.
Right. A 1,024 token experiential context from a 150,000 vocabulary size yields a theoretical upper bound of 17,600 bits.
Wow.
That is over 5,000 times the bandwidth of a discrete scalar reward. But since the teacher is conditioned on this text during training, do we still need the coach or the context at inference time?
No, you don't, because the technical implementation relies on on-policy context distillation. The experiential knowledge is prepended as context to a teacher model.
Okay, so the student learns from that.
Yes. The system minimizes the token-level reverse KL divergence between the policy, the student, and this context-conditioned teacher. So the knowledge is entirely baked into the policy parameters.
What's fascinating here is that both RL and EL use the exact same feedback LLM.
Right, like GPT-4o or Qwen 3.8b.
Yeah, and the exact same rubrics. The capability of the evaluator hasn't changed at all. What changed is just how much of its insight is allowed to reach the optimizer.
But it's easy to claim that 17,600 bits is better than 3.3 bits. Does this actually change the underlying probability distributions the model learns?
Well, let's break down the paper's controlled toy experiment on distribution matching, because that answers it perfectly.
Yeah, the bimodal Gaussian mixture one.
Exactly. They set up a non-verifiable task where the true target is this smooth bimodal Gaussian mixture, but the reward is quantized into 5 levels.
And what happens with standard RL?
RL produces this jagged staircase distribution because all tokens at the peak plateau receive the identical maximum reward, so the optimizer just treats them all equally.
Right, it flattens the nuance.
But experiential learning, using direct distributional matching, perfectly recovers the smooth bimodal shape.
And we see this in the real-world benchmark proof, too. EL consistently beats RL on held-out wild chat prompts, AlpaCaval v2, Wild Bench, and Arena Hard.
Even when evaluating with totally different models like Qwen 3.8b and Olmo 3.7b.
If we connect this to the bigger picture, there is a fundamental philosophical difference between the two paradigms here.
Yeah, how would you define that?
Well, RL is reward-seeking. It will exploit literally any feature correlated with a higher reward, totally ignoring nuance. EL is distribution matching. It stays close to the teacher's distributional shape, so it retains fine-grained distinctions and inherently resists reward hacking.
Actually, there was a really surprising data point from the paper on that. EL actually achieved a smaller score improvement on the training set compared to RL.
Wait, really? It scored lower on the training set?
Yeah, but it massively outperformed RL on out-of-distribution unseen tests. Like, it had a plus 5.5 win rate jump on AlpaCaval.
Oh, wow. That makes sense, though.
Right. RL was essentially overfitting to the training rubric's basic reward hacking, while EL was actually learning how to be a genuinely better model.
But if passing textual feedback is the key to matching distributions, why do we even need the coach to distill it into experiential knowledge first?
Yeah, why not just dump the raw critique directly into the context window and save a step?
Well, the researchers actually discussed that in their Ablation studies. They tested feeding the teacher the full critique, which is the exact scoring output of the judge, and also rubrics only, with no response-specific feedback.
And what happened?
Both of those degraded out-of-distribution accuracy on IFEVL.
Oh, so it actually hurt performance on unseen instructions.
Exactly. And they also explained the iterative teacher ablation. If you update the teacher model each epoch, it improves in distribution scores, but causes catastrophic forgetting of general instructions.
Oh, man. So how do they fix that?
The fix is mixing in general domain prompts, like Tulu 3, for standard on-policy distillation without the experiential context. That stabilizes the model.
They also mentioned the multiple choice ablation, right? Where they give the coach just 9 predefined directives.
Yeah, and while it preserves ode performance, it gives very limited gains because its bandwidth drops right back down to roughly 3.3 bits, which is basically log-base 2 of 9.
This raises an important question about alignment, though. Like, why do raw critiques actually hurt the model?
It comes down to critique bias. The evaluation-oriented context biases the teacher toward generating text that sounds like a critic rather than a task solver.
Ah, so the policy just imitates that critic tone.
Exactly. It forgets how to follow normal instructions, and the model's overall capabilities degrade.
So what does this all mean for the ML engineers listening? I think the synthesis here is that the structure of the feedback matters just as much as the volume.
It has to be structured correctly.
Right. The text must be framed as generalized, forward-looking advice, that experiential knowledge, so the model learns the actual skill, not just the act of being critiqued.
Experiential learning really proves that for complex, non-verifiable tasks, we just have to move beyond scalar rewards.
You really do.
By utilizing an LLM as a coach and on-policy context distillation, we can train models with over 5,000 times the bandwidth. We are finally capturing the how and the why of good responses, not just the what score.
It's incredible. And I want to leave you with a final concept to explore on your own. If a policy can successfully internalize the abstract, generalized strategies of a coach directly into its weights without needing that coach at inference time, what happens when we scale the diversity of the coaches?
Oh, that's a wild thought.
Right. Could we post-train a model by feeding it experiential knowledge extracted not just from GPT-4o, but from domain-specific expert models?
Like an ensemble of coaches.
Exactly. Creating a single policy that has internalized the distinct, specialized problem-solving strategies of a dozen different expert coaches.
That would be incredibly powerful.
It really would. Thank you for joining us for this deep dive into the paper. Keep experimenting, keep pushing boundaries, and stay up to date with the latest in AI research. Catch you next time on AI Paper Slop.